Color applications. Here are your priming questions. So, some of you have probably been thinking that what you learned in art is different than what you've been learning here. In painting or in art, you have three primary colors, red, yellow, and blue, whereas I've told you that for physics we have three primary pigments, yellow, magenta, and cyan. And you probably were wondering why, and if you think back to art, whenever you combined your three primary colors, you could never get a true black. Instead, it would always come out as a brown. And that's why, because of the limitations of having these three as your primary pigments. When you have cyan, yellow, and magenta, you can mix them in amounts to be able to get a pure black. And if we think of what a pure black is in this case, it absorbs all colors of light. If we had a true black pigment, we would see it as a pure void in space because no light would be reflected from it. It would be absorbing all light. This is one reason why we call black holes, because they appear to absorb all light. In the visible light spectrum, it does not reflect or release any visible light. So, we're going to go through some different applications for our understanding of color for the sky. So, why is the sky blue? That's probably what some of you have thought. And some of you might have heard it's because it's a reflection of the ocean. And then you say, why is the ocean blue? And you say it's a reflection of the sky. For this understanding, we need to go back to chemistry with what you learned about the Tyndall Effect. The Tyndall Effect is the scattering of light based off of the size of the particles. Now, if we think of our Roy G. Biv, our red and orange are going to be our longer wavelengths. The longer the wavelength, the larger the particle that it reflects off of. Biv, blue, indigo, violet are the short wavelengths. These reflect off of small particles. And then the yellow and the greens, these are going to be for the mid-sized particles. So, with the Tyndall Effect, going back to chemistry now, depending on the size of the particles, it will determine which wavelengths of light that it is able to reflect or to scatter. This can also be used for Rayleigh scattering if you've learned about that, but we're going to keep it simple and just talk about the Tyndall Effect for that. And so, our atmosphere is primarily composed of nitrogen and oxygen, and if we think of these are N2 and O2. These are relatively small particles. So if you think of this, these will typically reflect violet and blue light. So this is why we typically perceive the sky to be blue. It's actually also violet, but we can't see violet as sensitively. And we primarily see the blue color there. And also, if you've ever seen pictures of the Earth from the moon, you'll see a blue glow emanating from the Earth like this. So this is going to be primarily composed of oxygen and nitrogen for the atmosphere, and it's scattering the blues typically that we see better. We see those blues better, and it's scattering those blues because of the smaller particle size due to the Tyndall Effect. So, for rain, if you think of the sky before a good rain, you should see that it's a fairly pale blue, almost grayish even. After a rain, if you look at the sky, you'll see that it's a deep blue. So the question becomes, and we'll talk about this in class, is what does the rain do to the sky that makes it change from a perceived pale blue to a perceived deeper blue? Next is the sunset. The sunset appears to be reds and yellows and oranges, which, if we think about, that's on the Roy side, which means for us that it's going to be the longer wavelengths of light, which you might think that means that there are bigger particles that are scattering, but hopefully this diagram will help you understand what's going on. So think of the green as the Earth itself and the blue portion around being the atmosphere. When the sun is overhead, it's only going through this much of the atmosphere. But when it's a sunset, it's going through a lot more of the atmosphere. And we just said that the atmosphere composed primarily of nitrogen and oxygen, scatters the higher frequencies of light, the blue, indigo, and violet. And if we think about it, what that means is that it is going to be taking out those wavelengths of light, the blue, indigo, and violet, and even some of the mid-level ones. And so, for our understanding for this, only the longer wavelengths of light are able to penetrate through that much of our atmosphere to be able to be seen by our eyes. And so it's because the blues are reflected by our atmosphere that we perceive our sunsets to be red. Now, clouds. So you probably are thinking about clouds. Clouds are what color? They're typically going to be white, which means for us that they are reflecting all wavelengths of light. So if you think of what clouds are made up of, they are made out of water particles of all sizes. So if we think back to the scattering of light, if we have particles going from the very small, from a single molecule, all the way to a full droplet, which could be hundreds of thousands, if not millions of molecules of water, it is going to be able to reflect or scatter all the wavelengths of light, which we will perceive to be white. Now, our ocean. If we think of our ocean and the water, the color is cyan, roughly. Now, if we think of what cyan is, it is blue and green. So the blue and the green, as light hits the water, the blue and the green light scatters quickly to a pretty shallow depth. So it reflects off of the water to a pretty shallow depth. And if we think of this, where does this blue light come from? Okay, we'll talk about that in class. In this case, we also talk about the reds. The reds penetrate through. And if you think of some of the adaptations that some of the crustaceans have made, think about what color the shells typically are and why they might have red for that pigment. Now, for our sun appears to be yellow. And if it appears to be yellow, this is going to be a secondary color and light addition, and we perceive it to be yellow because we see red and green, which means what we're seeing is red and green coming through. And if we think back to the sky, we said the sky scatters our blue light, if we think just of our primary colors. So that means that the only other primary colors that are left are going to be red and green that get to our eyes. And so we actually see red and green light coming from the sun, but we perceive it to be yellow because that's what our brain combines red and green light to be. So here are priming questions again. We'll discuss some more in class.